Okay. So last class, we started looking at the discrete random variables, and we talked briefly about the uniform distribution where everything's basically the same. Today, we're going to start looking at what's known as the binomial distribution. So to start with the binomial distribution, we need to know what a binomial experiment is. We've talked slightly, kind of about this at 1.4. Binomial means there's only two outcomes. So true, false, heads, tails, those type of things. So therefore, basically rolling a die, would not be a binomial experiment because there's 6 possible outcomes to that. Yes.
Say, like, if you converted it to like 1, 2, 3 versus 4, 5, 6, would that be right?
So yes. So as long that's actually where I was going to go next.
Oh, right.
So that's okay. So if I said, did I roll a 6 or not? That's now a binomial experiment. Okay, because now it's a I won or I lost type situation. Or if I did evens and odds, that would be a binomial type situation. Okay, so I can turn a dice game into a binomial experiment. I can do a lot of things like that. I just have to somehow make it a win-loss type situation, or an A or B situation where there's only 2 possible outcomes. The experiment consists of a number of trials, so more than one. The probability of success on any one trial is denoted by P. So that is the probability of success. And the probability of failure is 1 minus P. So basically the complement of it. Since it's a one or the other, that's how that works. If it wasn't, we wouldn't be able to just find the complement. The trials are independent, which means they don't interact with each other, so there's no overlap between the trials. And the binomial random variable is the count of the number of successes in the experiment. Okay. Any questions with that? All right. So give everybody a second to finish writing it down. Before we do some problems. All right. I see people still writing, so I'm waiting. Because I know if I switch, somebody's going to say, go back. All right. This is the act. Do not write this down. This is the formula to do the calculations of it. As with all the rest of the formulas so far I've told you that are complicated, I'm going to give you a calculator that doesn't. The calculator is actually already linked on my website in the post for chapter 7. So if you notice, basically the things that you're going to need to know are down the bottom. So we need to know those things down there. Those are the 3 things you're going to need to know for any problem. You're going to need to know the number of trials. You're going to need to know the probability of success and the number of successes of n trials. So however many successes you want to have in that situation. So big complicated formula. Don't worry about that. So this is the calculator that we're going to be using. And the only difference on it is they use K for the number of successes instead of X. So those are the three things you need to know. Probability of success, the number of trials, and how many successes you wanted. Okay. All right, so let's look at this. Toss a coin 4 times, record the number of heads. So is the number of heads in 4 tosses a binomial random variable? Yes. Why?
Because it's a number of heads, not if they have heads. Like it's not a, there are more than one answer. It won't be just true or false. It'll be like how many heads.
Like there's no success failure.
Okay.
Yeah.
So all right. When I flip the coin, how many outcomes are there? 2, right? Heads or tails. Or in essence, heads and not heads, right? Okay, so that's binomial, correct? Okay. Don't focus on the 4 tosses yet, because the 4 tosses is how many trials I'm doing.
Right.
Okay. So the second thing we want to look at is how many times am I doing the experiment? In this case, I'm doing it 4 times. So n in this case is 4. What is the probability of getting a head? Yeah, 1/2. Okay, so it's heads and not head. Those are my 2 options. If I flip a coin and I flip the coin again, did the first flip have any impact on the second flip? No. So one outcome is not going to do the other one. Now, what's the variable that I'm interested in? So it's the number of heads, right? Okay. All right. So if we look at this, so here are all the different ways that I can flip 4 coins. All right. So how many heads were in the first one? Yeah, the first event. 0 heads. How many heads are in these 4 events? So there's 1 in each one, right? So 1 head. And that one. And then. Okay. All right. What's the probability that I'm getting 0 heads? How many events are there? Nope, there's multiple events in each row. You're right, there's 5 rows, but there's multiple events. I think you counted off. I think it's 16. Yeah, 16. All right, so how many was in the first row? 1. How many is in the second row? 4. Third row? 4th row. And last row. 1. All right, so in a situation like this, it's really easy to sit there and list out all the possible outcomes and get my answer in that respect. However, not all situations are going to be nice and easy that I can easily do that for. So the question, so it comes in and it's like, okay, let's see how these numbers actually work. So let's go back to this situation. What was the probability of success for my coins? It's 1 out of 2, right?
Yeah.
So all your numbers have to be in percentages in this case, or as a decimal. So 1/2 would be 0.5, correct? Okay. How many trials did I do? It was 4, right? I flipped the coin 4 times. Okay. And let's take 2 heads. So the probability of getting 2 heads is 0.375. All right. So 2 heads was 6 out of 16. And if you divide that, you get 0.375. Okay. So what this calculator does is this first one right here, it's telling me the probability that I would get 2 heads out of that number of trials. Okay. It also gives me some other information. It tells me what the probability of getting less than 2 heads is, less than or equal to 2 heads, greater than 2 heads, or greater than or equal to 2 heads. So it gives me all those different options depending on which direction you're going, depending on what the question is asking you. Okay. All right. So it verified that the calculator works and gives me what I want. Now let's use it. All right. Roll a 6-sided die 4 times and record the number of 6s observed. So, first question. Is this experiment a binomial experiment? Why?
if they give you one time.
Okay, so what am I looking for? So, okay, so for it to be a binomial experiment, I need a success and I need a failure, right? Those 2 things. For the way that they worded this, what would be a success? A 6. What's a failure? Not 6. That makes a binomial. Since I'm only caring about the 6s, that's the definition of success, is I get a 6. The definition of a failure is anything else. Okay? Does that make sense?
Yeah, I was just caught up on the number of trials changing.
I know. So that's my success, that's my failure. What is my probability of success? So what is P? What is the probability of me getting a 6 on a die? Standard die. Yeah. 1 out of 6. Give it to me as a decimal because it's going to want it as a decimal. So divide it.
0.16.
All right. So 0.167. All right. How many trials have I done? I did 4 trials. Okay. And they want us to construct a probability distribution. They want a probability distribution. That means I need to have all the possible outcomes. So remember, X is my successes, right? So I can have no 6s. I can have 1 6. I can have 2 6s. I can have 3 6s, or I can have 4 6s, correct? That's the only ways that I can have that, right? Everybody get that so far? Okay. So now we're going to go to my calculator. and I want no sixes. So my number of successes is 0. Calculate. So the probability of getting no sixes is 0.48148. Does that number make sense to you? Yes. No.
Almost half. You repeat it again? It's almost half, but there's 6 numbers.
So if I'm rolling a die 4 times, what that number represents is the probability that I'm going to get no sixes on any of those 4 rolls. Okay. So probably I'm going to get 0 sixes on those 4 rolls. Yes.
It doesn't look
Okay.
right. That's almost what, like a 50% that you're
Mm-hmm.
the initial chances are 1 means that
All right. So to figure this out, actually, you know what? Let's do it this way. Let's get the rest of them. Okay. And then we'll see how this works. Because you got to remember, what are the odds of me getting a 6 on 1 roll? 1 out of 6. And there's a 5-6 chance I'm going to get no 6 right in that roll, right? And there's a 5-6 chance I'm going to get no 6 on the next roll. And on the next roll, there's a 5-6 chance I'm not going to get any 6s, right? So hold on, let me actually do this for math real quick. That's not what I wanted. So if we go back to our, okay, good. We go back to our probability, right? 5-6 chance on the first roll, 5-6 on second, third, fourth. So we multiply 5-6 times 4 times, right? Which is what I did there. I just used an exponent, and that's what I get is that percent. So it seems high, but you got to remember the chance of you getting a 6 is a low chance. So when we were looking at a coin, the chance of you getting a head is a 50-50 shot. So that's 50%. And now we're at a 0.167. So it's a lot lower of a percent chance. Okay. So that's where that 48% chance or 0.48 comes into play. Does that make sense? All right. So since this is a probability distribution, we need to come up with the rest of the numbers as well. Yes.
the same thing, but like reduce what power it's gone to?
No. Because, well, actually, yes, you can. We do 5-6 times 5-6 times 5-6 times 1/6. So yes, you can. But again, that works well in a very small situation. So you got to remember, it's like these are working when we're looking at but if I said, what's the probability of me getting 7 6s on 50 rolls? Now that's becoming a lot more complicated. And actually, believe it or not, that's what that formula does. That formula is exactly what you just did. The successes, the failures, and how many I'm choosing is there. So that's in essence what that formula is doing. All right. So if we did the same concept, if I did the 1 there, I get 0.3611 for the probability of getting 1/6. Yes.
Is it adding or multiplying that extra?
It's multiplying. But so you would get that if you multiplied it straight out, right? That's not the answer we got. Because how many different ways can I get that 1/6 in the thing?
Oh, right.
I can get it 4 different times. Okay, so that's why I said doing this out is fine. That's what that formula does. So what the formula does is in essence, it's doing the NCR of 4, choose 1. And then with the exponents up here, that's the 1 there because you had 3 failures and 1 success. And then if I'm doing 2, I would do the 2 there. I have 2 successes and 2 failures. So that's what that formula does. And that formula will work for anything. Like you can do that. Like like I said, you wanted to do 50, I can change this to 50 and I have 48 successes and 2 failures. So I can even do it like that formula will always work. The piece that's going to be more confused, the piece that the formula doesn't really help you with is when you start looking at multiple situations, which we're going to get to in a little bit, where you want to combine things, where the calculator, this one that works out really nice, is it gives me those other values that are going to be helpful later on. Because to figure out less than 1, I would have to figure out 1 and 0. To figure out less than 3, I'd have to figure out 2, 1, and 0. So I'd have to figure out multiple values to come up with that. So, all right. So let's fill in the rest of the table. So 2.
So is it that first one or?
Yes. So in this case, we're looking for exactly 2 outcomes. That's okay. I'm going to switch back over in a second. I'm going to have them all there. I'm just copying and pasting them over to the other screen. And 4. Yes.
Usually ask us to round to the third decimal place. So in this one, would that just make it 0.001?
Yes.
Okay.
Yep. Anybody ever play Yahtzee? So you roll 5 dice in Yahtzee, right? And if you want to get all of them at one shot, that's the probability of getting Yahtzee on your first roll. Not a very good chance of getting Yahtzee on your first roll. That's why you get 3 rolls. All right. So we've got, that's what my probability distribution is. It gives me the values of each of those broke down. So what's the probability of me getting 2 or less 6s? So I want the probability that X is less than or equal to 2. Yeah.
Just add the two together.
Yep. I'm going to add that one, and that one together. That's what I come out with. So that's where that calculator comes in to really become helpful. So you wouldn't have had to do it 3 times, or you wouldn't have had to do that formula 3 times. The calculator will actually do that calculation for you and combine them all for you. So you can do those higher degree ones. All right. Okay. What are the two pieces of information that I always seem to find for things? What are the two things that we talked about a while ago that I always seem to keep coming back to? One starts with an M. Yeah. Mean. And what's the other one? Standard deviation. But yeah. All right. So these are the two formulas you're going to have to write down. These you will actually use. And because they're not that overly complicated to do. So mean is your expected value. Remember, mean and expected value are the exact same things. So mean is just your n times p. Okay. So it is the number of trials times the probability. Okay. So it is the number of trials times the probability. Your standard deviation is the square root of the number of trials times the probability times the complement of it. So 1 minus p. All right.
Go back.
Sure. Mhm. All right. So if anybody ever wonders how they determine who's going to drill for oil on certain properties, this is how they do it. They literally hold a lottery, and then you get to, if you win, you get to lease those pieces of property. So your company has won the rights to 12 leases. Historically, about 10% of these lands possess sufficient oil reserves for a profitable operation. Okay. So we're not going to construct the probability, but it's okay. We're not going to construct this. We just did that one. What's the probability that at least one of the leases will be profitable? So what are the three pieces of information that I need to know? Not you. Somebody else. What are the three things that I need to know for these problems? Yes.
So you have to know. Like the property.
Yeah. What are the three things that I need to know?
So the 12 leases.
Is what?
Apple at now.
Okay. So the 12 leases is one piece of information. What part of that, what piece of information is that the 12 leases represent? Yes. That is my number of trials. So that is it. So one thing you have to ask before you even do this. What do we have to make sure that it is? We need to make sure it's a binomial experiment. Is there a success? Is this a success and failure situation? Yes. Okay, so we're good. All right. So we've got 12 leases. That's the end. That's the number of trials. Okay. All right. What other piece of information do I need to know? What's the only other number in this problem that's actually written out as a number? The 10%. And what's the 10% represent? That is my probability. So the probability of success is 10% or 0.1. All right, so that's the probability of success. Okay, we need one more piece of information. There's three things I have to plug into that calculator. Yes, go ahead. We're going to find that in a minute. But
Oh, it's the condition, right?
okay, what's the condition?
Uh, enough oil to be profitable.
Okay, but that's not going to give me a number.
A number of six.
Right. We have how many successes do we have? Are we looking for? Almost. At least one, which means we're looking for greater than or equal to 1. So I've got 7. I want at least one success.
So X would equal.
Is greater than or equal to 1. So we go to our calculator. My probability is 0.1. Number of trials was 12. And the number of successes I want would be 1, because it's going to come up and calculate the thing down here for me. We want greater than or equal to 1. So it is 0.71757. Does that make sense? Yes.
How is that the number of successes is 1? Is it just the probability? Or
Yeah, it says the probability that at least one of the leases would be profitable. So since it says at least one, that's what we're looking for is X is greater than or equal to 1. So in the calculator, I'm not going to plug in 1, 2, 3, 4, 5, all those numbers. I plug in the 1, and then down the bottom, it gives me the greater than or equal to 1 that I'm looking for. What's another way that I could have done this problem? Yeah.
Complement.
What would be the complement of this one? Oh, yeah. Okay. You don't want to go that direction. Yes, you don't want to go that direction. What's the so if I want greater than or equal to 1, what's the complement of that? 0. So in this one, I could have just calculated 0 and subtracted it from 1. So I could have put in here no successes, and that would have given me that. And I could have just said 1 minus that, and that would have given me the exact same answer. Okay. But the nice thing about this calculator is it does those calculations for me automatically, so I don't have to worry about that piece. If you were doing this out with the formula, I would have definitely said to find the 0, because you would have found one answer instead of having to do it 11 times. So, all right. Let's find my mean and my standard deviation for this one. What's my mean? So what's the formula for mean? Yep. So n times p. So 12 times 0.1. So 1.2. And what's my standard deviation? So what was n? P was 0.1. And what's 1 minus p? This is where you're going to use the 90. So 0.9. One key thing, these two numbers right here always have to equal 1. Okay? Those two numbers should always equal 1. If they don't, you messed up somewhere. So I would use Desmos for this. And my suggestion, especially when you're working on your homework and you have to do a bunch of these, is I would do this. I would have so I would have NP, and then I would have the square root of N P 1 minus P. And then I would put in the numbers here, and it will do the calculations for you. This way you can just keep changing the N and the P to do all your problems for your homework. So you don't have to keep changing the formula and type the formula back in a million times. And that'll always give you your mean and your standard deviation in one shot. Okay. So like, for example, if we did 4 trials on the dice, and actually with this one, you can actually put in 1/6. So the mean of that thing was 0.67, and the standard deviation was 0.74. So you can just easily change these numbers to give you what you're looking for. Okay. All right, your turn. All right, find me the answers to these 3 questions, or these 4 questions. Oh, I switched back over, huh? There we go. Go to my website, but let the calculator there so you can actually put that in. calculator, you don't have to go search for it. It'll work on your phone too.
Which calculator is it?
It's the binomial distribution calculator. Should be the one, the second one in that list on the first post. So what are the pieces of information I need? I know you have the answer.
The number of trials, 12.
Why is it 12 and not 1,001?
Who you're choosing from, not from where you got the data from.
Well, actually, the 1,001's actually where they got the data from.
Yeah.
The 12 they're choosing from that. So that's some of these problems are going to give you more information than you need, and it's really easy to screw that up. I will tell you, here's the nice little thing is when you actually, if you looked at did the calculator and you put in 1,001 here, you're going to get a whole bunch of zeros. And it's like, wait, something's wrong here. And then try the other one. All right, so that's the number of successes. And I always I forget to ask this question. Is this a binomial experiment? But I have 3 percentages here. So what's the success and what's the failure? Okay, so success is eat to live, and failure is anything else. Okay, so that, again, you have to think about that sometimes because depending on how they worded it, if it said live to eat, it would have been different. Or it would, like, you have to think about what way they're looking at this problem. So, all right, so eat to live. So my probability is going to be what? Yeah, so 0.74. And then in this case, my x, for the first one, x equals 7. What about B? So no more than 10. How am I writing that one? This is where that less than or equal to, greater than, those come into play. Making sure you're picking the right one. What does no more than 10 mean? Can it equal 10? Yeah, less than or equal to. At most 11. Less than or equal to, greater than or equal to, less than or greater than. There's only 5 options. Which one? It's less than or equal to 11. So yeah, at most and no more than kind of mean the same thing. At least 3. Go ahead.
Was it greater than 3?
Almost.
Greater than or equal to?
Yeah. As you can see how these problems aren't necessarily always going to be just plug in the calculator to get your answer. Like you have to do some calculation or some reasoning behind where that's coming up from. That's why I don't mind giving you the calculator, because that's the least of the actual problem. It's like actually understanding what they're asking for and where to get it. That's actually just as much of a problem. All right, so the first one we get was 0.11 for 34. Because that was equal to 7, because it was exactly 7. The next one was less than or equal to 10. Yep. So that's there. Next one was less than or equal to 11. So 0.9730. And the last one was greater than or equal to 3. So almost 1 in that situation. Yeah.
For that one, we don't round up, right? Because then it would be 20.
If they ask you the question at that point, you would say technically it would round to 1. If they want only 3 decimal places, it would round to 1, yeah. All right. So. Okay. Let's look at one more uniform or one more distribution. All right. The next distribution we're going to look at, we kind of looked at this before. We looked at a discrete uniform distribution. This one is a continuous uniform distribution. So what is the difference between discrete and continuous? Yeah.
I mean, like,
Yeah, it's everything between the two values works. So when we were looking at the discrete one, we had breaks, right? We had the different spots in there. So we had the different breaks in there. So it was like 1, 6, 1, 6, 1, 6, 1, 6 all the way across. However, in a continuous distribution, we're going to have the entire thing all the way across. Every one of those values works. So we can't determine like specifically like what's the probability of 1.13, 1.15. Like, so that's where your uniform distribution comes in. Since everything is absolutely going to give you the exact same answer, we can make it as a rectangle. When you're looking at the value of it, we would be looking for a value between two numbers. So you'd look for the probability between, say, 5 and 6, whatever it happens to be. Okay. And that's how you'd actually figure out your probability in there. So that's where this comes into play. Okay. So the height is always the 1 divided by whatever the range of the values are. So from B to A. So that's the height. And that's also would be, because by definition, the height is going to tell you whatever your probability is. So that is basically your probability of that occurring. Your mean, these are the two things we always look for, is A plus B divided by 2. 2 endpoints, add them up, divided by 2. That gives you the exact middle of the value. And your standard deviation is B minus A divided by the square root of 12. Don't ask me why it's the square root of 12. But it is always the square root of 12. It is not, that doesn't change. Okay. I would rather not have to try to teach you calculus to figure that piece out. All right, so the 3 pieces of information you need to know: when we get the A and the B, we can figure out the probability, which is the height. We can figure out the mean, and we can figure out the standard deviation. All right, so Firebird chart records how long it takes each of its trucks to reach the scene of a fire. So, the minimum amount of time it takes is 2 minutes, and the maximum amount of time is 15 minutes. Okay. So, if we set up our wonderful little thing here, so that's 2, and that's 15. And that's my uniform distribution. Because it can show up anywhere between 2 minutes and 15 minutes. We don't know, one value is not higher than another. It's an equally spaced thing. So, what is the height? So, what is the probability that any one time would occur? How did I find that?
One divided by 15 minus 2.
Yep. So P is 1 divided by 15 minus 2, which is 1/13. When you're doing these problems, if it's already in like a fraction form like this, leave it as a fraction until you do the calculation that you're going to use it for. Because if you change that to a decimal, you're going to have to round to that one, and then you're going to round again later on, and it could cause issues. So, like I said, fractions are nice in this situation. And again, you're using calculators, so the fractions are not the end of the world. All right. What is the probability that a truck will reach the fire scene between 5 and 10 minutes? So I want to know, now I'm just going to copy the actual picture. This is a nice picture. So I want to know between 5 and 10 minutes. So how do I find the area of that box? How do you find area of a rectangle? Yes. Length of width, or height and width, right? So what's the height? We know is 1/13, right? So it's 1/13. And what's the width? 10 minus 5 is 5. So the probability that's between 5 and 10 is 5/13. What's the expected response time? Or what's the mean? What's the formula for mean? So in this case, it's going to be 15 minus or plus 5. No, sorry, not 15 plus 5, 15 plus 2. Divided by 2 is 8.5. What's the formula for standard deviation? Square root. All right, so it's 15 minus 2 over the square root of 12. So this is what we need to use Desmos for. So on the calculator, it's the check mark symbol right there. So 3.75. All right, last one. I don't want to do that one. We'll do this one. All right. On average, what time does the employee arrive? So what do we need to figure out? What are the pieces of information that I need to know for this problem? I need A, B, and I need my probability at some point, right? So what's A? Okay, so 8 a.m. is right. Yeah, we'll use 8 a.m. It's fine. And then what's B? Right. So if I use 8:30 and when I'm trying to do my subtraction, it's going to be a pain in the butt, right? So let's use 8.5. That's why I was debating on just using 0 for A and 0.5, but then I'm like, now we can use 8. All right. So what is my, so now that I've got that, I can figure out my probability, right? So what is my probability? Which is what? 2. So the height of my rectangle is 2. Or actually, we really probably shouldn't call that probability because probability can't be greater than 1. We'll call that height. It's not going to change any of the work later on. So, all right. What is the average time the employee arrives? How would I do that? How do I find average? Add them up and not multiply by 2, divide by 2. What am I adding up to? So, is this a uniform distribution? Continuous, yep. So what was the formula for average or mean? Remember, average, mean, expected value, all the exact same thing. Okay. So mean is 8.5 plus 8 divided by 2, which is 8.25 or 8:15 a.m. Don't put that at 8:25. I have seen people get that wrong in Hawks because that's exactly what they put. Remember, we have to change it back to time. The quarter hour is 15 minutes. So you know why we use 60 minutes for time?
Fun fact or something we-
It is not something you need to know. If anybody knows it, though, I'll give you an extra 20 points on your next test. Why do we use 60 minutes for time? Huh? I'll give you 2 minutes. And searching Google isn't going to get you the 20 points. Why do we use 60 minutes for time? And in essence, the same for why we use 60 seconds. 1 minute left. Yeah.
Does it have something to do with the 24 hours of the day? And
Nope.
Have something to do with like the fraction, but easier time. An hour.
No, because actually it'd be easier if it was 50.
yeah.
Way easier if it was out of 100. That's kind of why I asked the question. I'm like, well, why do we use 60 instead of 100? Oh, no, there is a reason. The odds of anybody in here knowing it were very slim. It has to do with Babylonia. Babylonians basically set time and they used a base 60 count system. They had numbers or symbols for everything from 0 to 59. Actually, not 0, sorry, 1 to 60, because they didn't have a 0. So, and they were the ones that created the actual calendar and the time system. So, I'll give him a call back as soon as I'm out of class. All right, so that's why. Okay. And we just have never changed it. What is the standard deviation? Yeah.
Would it be the 8.5 minus 8, 5 minus square root of 12?
Yep. So let's give me my number there so I can write it down. 0.144. Which I do not know what that translates into time at the top of my head. Let's see, hold on. 60 is 8.6 minutes.
So what is 0.6?
36 seconds.
Oh, yeah.
All right. If a call comes in at 8:10, what's the probability that the employee will be there to take the call? So what times would she'd have to arrive by what? To take the call at 8:10. Yeah. Oh, we'll do 8:10 just to make life a little bit easier. All right, so she has to arrive by 8:10. So what is the time? So it's 10 minutes, right? Divided by 60. So 0.167. So 8:10 is 0.167, and it's times my height, correct? Which is times 2. So 0.333 is the probability that she would be there, that it's less than or equal to 8:10.
Not a colon after that or a decimal?
Oh, that's a colon. That's 8:10 a.m. That's the problem when you're dealing with time, is that it's not out of 100. So it makes it really hard sometimes to do those calculations. All right, last one. Can you find me the probability that the employee will arrive at exactly 8:10? Huh? Nope. Based on what we've done, can you find the probability of an exact time? So figure out this one that we just did, right? What did we do to get that? We did 8:10 minus 8 a.m., right? Which gives me the 10 minutes, which we changed it to the 0.167, right? So we subtracted 2 numbers to get that. So if I did 8:10 minus 8:10, I get what? 0. So the way this is set up, you can't find the exact value for an exact piece because you need width. You need some number at the bottom to be able to multiply to figure out the height. Most of the time, what they will end up doing is they will do the half on either side. So we would have looked for, in essence, 1 minute, which would have given me the time from 8:09 and 30 seconds to 8:10 and 30 seconds. And that would have been how they would have actually done it. But you can't find the value for an exact time. Yes.
Would it have worked if we saw it like discreetly instead of like
Oh yeah, if it was discrete, absolutely. Yeah, absolutely. If you could have done discrete, because then each time would have had their own
Yeah, okay.
arrival time. So, but since this one is a continuous, we don't have that exact thing. So, all right, we're done. Have a wonderful spring break. I will see you afterwards.
On home.